Hello class, welcome to the next video in the calculus series. So we're looking at lesson 13, related rates. So in the previous lesson we looked at implicit differentiation. We looked at the derivative, we looked at derivative techniques. Now we're going to apply what we've learned as far as the derivative is concerned to word problems. So we're going to be looking at some applications known as related rates. So we had talked about the chain rule and implicit differentiation. So remember that the chain rule was used for implicit differentiation. For example, when we have the equation 3y squared plus 5x equals 9, what we did was we took the derivative on both sides implicitly. Implicit means that y is not solved for by itself. Y is not isolated. You have the variables mixed together on either side, in this case on the left side. So we want to be able to take the derivative of that implicitly. And so if we did that, well, the derivative of the 3y squared, right, is going to be 6y, but we have to make sure to do the chain rule. So we need to take the derivative. We just have to make sure that we take the derivative of y with respect to x. So this part right here is the chain rule part, right? So this is the chain rule. And then the derivative of 5x is equal to 5. And then we isolate the dy dx, right? And we solve for it by moving the 5 over on both sides and then dividing by 6. And so we get our explicit form for dy dx. And so instead of differentiating with respect to y, sometimes we're interested in differentiating implicitly with respect to time. So here we were differentiating with respect to x. So now we're looking at related rates. Rates meaning time rates, right? So rates related to time. In this case, one or both variables might be actually changing with time. So in this example, x could be varying with time, and y could also be varying with time, right? Rather than y varying with x, okay? So in this example, y varied with x, which means that we took the derivative with respect to x. But now we're going to swap the x out with time. And so that's what we mean by the related rates. So suppose we have a cone in water in which water is being poured. We got the water level varying over time. How much does the volume vary over time? So that's an example of a rate of change, right? Rate of change with respect to time. So we're looking for a volume, right, over time. So we know that the volume of a cone is 1/3 pi r squared h. So if I have, for example, if I have a cone, right, and I know the radius of the cone, I know the height of the cone, then the volume is going to be 1/3 pi r squared h. And so if I take let's say that the volume varies with time, right, because we have water being poured into the cone, for example, well then the volume of that water level is going to change, right? So we're going to say that the radius of that water cone, if you will, it varies with time, but also the height, right? The height is changing over time, and it's increasing. So that's the main idea. And so we know that the volume is going to vary with both variables. Okay, and so that's what we mean by the related rates. So we're introducing the time element into these applications. So suppose we have a cone in which water is being poured. So the example that we looked at. So we know that volume is 1/3 pi r squared h. And then we know that we could take the derivative of the volume with respect to time. And so now that we know that both variables change with respect to time, we can take the time derivative. So the derivative with respect to time is the same as any derivative. It's just you're just using t instead of x, right? So we take the derivative, and then we also have to keep in mind the chain rule when we do this. So we know that the derivative of r squared is 2r. But since r varies with time, we need to make sure that we include the chain rule, right? So we need to take the derivative. We also have to multiply by the derivative of r with respect to time. Now, if you have a question on the chain rule, go to the previous lesson when we talked about the chain rule. but in here, we're just going to assume that you know the chain rule for this part. And then we're also going to take the derivative of h, right? And the derivative of h is just 1. And then, but then, so we know that the derivative here, there's a 1 here. But then, since we took the derivative of h with respect to time, we need to include that time derivative, all right, with the chain rule. So this is another chain rule here. All right, and here we're using a product rule. PR, the product rule, because we have two variables that are, we have a product of two variables, right, that we're taking the derivative of. Okay, so in this case, the rate of change of volume of the water level is related to the rates of change of the heights h and r, and hence the term related rates. So here we're when we have that a relationship between the two variables here, height and radius, which both vary with time. This is what we're talking about with the term related rates. Okay, so so here's an example of this, what I was trying to draw earlier. So you have the radius here, r, little r, which is changing with time, and it's increasing as the water level is going up, right? Then the height with respect to time is increasing, but also the radius is increasing as well, right? Up until the point where it maxes out at the capital R radius. And then we have the capital H, the height, the ultimate height of the cone. All right, and we know that the water level of this, or of the volume of this water cone, the water part, is the shape of a cone, and it's varying with time. All right, so example 1, let's look at an example. We'll switch away from the cone for a little while, and then we'll switch back to the cone in another example. So for this one, we're looking at x and y being both differentiable functions of t, and we have an equation, right? X squared plus y squared equals 25. So these vary with time, right? And so we're going to go ahead and find dy dt as long as we know x, y, and then we know dx dt. So we're going to need to take the derivative of this equation with respect to time on both sides. So here's the equation. Let's take the derivative with respect to time. Now we know the derivative of x squared is 2x and the derivative of y squared is 2y. Then don't forget to include the time derivative, so times dx dt times dy dt, because of the chain rule. We know that the derivative of a constant is 0, so we know that this goes away. That becomes 0. So here we go. We don't forget that the time derivatives there because of the chain rule. And then we're going to solve for dy dt. So we're going to isolate the dy dt, moving the 2x dx dt term, subtracting that on both sides. Here and here. And then dividing by 2, of course, right? 2y. Rather. All right, and so that basically turns into negative x over y dx dt. So there's our equation for dy dt. Now we're going to go ahead and substitute. We know that x is equal to 3, so we're plugging that in. We know y is 4, and we know dx dt is 8. And so our rate of change of y with respect to time is negative 6. So that means that when it's negative, that means that y is the length, or the y is actually getting shorter, smaller, right? So that means that the y value is either decreasing or that length is getting smaller. Okay, so negative, right? So it's basically, or in terms of coordinates, that means it's going into the negative, so it's going down. But when you think about rates, you're thinking about the rate is sort of like decreasing. When we're thinking about length or something like that, if it's positive and you're talking about lengths in a problem, that means it's increasing, right? So that means that the rate is positive, so that means that the variable in question is increasing. So you can think of it that way when we're talking about applications. All right, so here we go. So let's go switch back to the cone example. So we got the same diagram for the cone, and let's look at a specific scenario with some numbers here. So the water level is changing at a rate of 0.25 feet per minute, and the radius is changing at a rate of 0.15 foot per minute, what is the rate of change of the volume of water, the water level, when the radius is 2 feet and the height is 3 feet? Okay, so we know the equation for volume of a cone, and we've taken the derivative of it, so we're going to go to that. We've done the derivative of the volume function with respect to time, and so when we do that, we get this expression, or this equation, right? So we've done this part before already. Now we're going to apply it. So we know that the radius is 2 feet, so we're going to be plugging that in for r here, right? And here as well. And we know that the height here is 3 feet, so we're going to plug that in. And then we're going to need to plug in now this says that it's changing at a rate of 0.25 feet. So what that's saying is that that's a positive value. That means it's increasing. So the water level is changing, so it's adding to it. You're adding that much to the water level. So it's increasing by a quarter foot per minute. And then the radius rate is positive as well. So that means that the radius is increasing, right, by 0.1 feet per minute. This is what I mean by positive versus negative rates. So you're going to plug that in. So that's going to be your dH dt and dr dt. Okay, so we got the negative 0.1. I didn't. So actually, they actually didn't say whether it was positive or negative. So it says that it's changing. So they didn't actually say whether it's positive or negative. It just says that it's changing. So it's not saying that it's increasing at the rate. So we got to be careful with that. So I mistakenly assumed that. If you read the first sentence, which I failed to read here, it says conical tank is being drained. So that means that if it's being drained, this has to be a negative rate, okay? And has to be a negative rate right there, okay? So so that means that we're going to, I'm going to circle that negative there to make sure that we include that negative. So these are actually negative rates since it's being drained. All right, so we just want to be mindful of the positive versus negative rates. So I apologize for that error earlier. So went ahead and put the negatives there, and we got the 0.1 feet for the dr dt, that's the radius, and then the dH dt was 0.25 negative. So when we plug in the numbers, we get negative 2.3 feet cubed per minute. Be mindful of the units here. We're doing feet times feet times feet, and then we have per minute, so that's feet cubed per minute, right? So be mindful of units when you're dealing with related rates problems. So that means it's negative, which means that we know that the rate of the water level is decreasing. So this is the rate of change of volume is decreasing. Okay. All right. So let's look at another tank problem, something a little bit more difficult. Just an extra set of steps here. So we got a tank where the radius of 6 feet and a height of 8 feet is being drained. So there's so it's being drained. So we have to keep in mind, of course, we have some negative values here for the rates. The radius is changing at a rate of 0.2 foot per minute. So I'm going to put a negative there. What is the rate of change of the volume of the water level when the radius is 4 feet? So it's very important to keep in mind that when they're giving you a bunch of quantities here, you want to keep it as R. You want to keep the variables the way they are, and then plug the value in at the very end. So you never want to plug the value in at the beginning, because obviously if you take the derivative of a constant, that becomes 0 or that changes things. So you want to make sure that you leave it as a variable and then take the derivative so that you can include the fact that it changes, and then you plug in for the variable, okay? So that's something that I want you to keep in mind. So when we use the equation for the rate of change of volume, now I want you to keep this in mind, right? When we have the cone, we know that the radius of the cone varies with time. So I'm going to put like an r of t here, I guess, if you will. You don't have to include that, but that radius is changing with time, and so is this little height. It's changing with time. But you can see that there's two right triangles, right? You see two triangles here. This is just half of the cone. So if I cut the cone in half, And so if we just look at the triangles, we can use similar triangles for that, right? So we can say that the rates vary proportionally, or the variables vary proportionally. So we know that that h is to 8 as r is to 6. So if we use similar triangles, right? So this is similar triangles. So using similar triangles, h is to 8 as r is to 6. And so we're going to solve for the height in terms of the radius. And so it's going to be 3/4 r. So this is our equation for h. And we know what r is. We know that the radius is 4 feet. So that means that the height has to be 3 feet. Okay, so we know that when the radius is 4, the height is 3 feet. And so next we're going to take the derivative of this equation. So let me just bring this down. Take the derivative of that so that we can get some time rates. So then if we solve for dh dt, it's going to be 4/3 dr dt. So you can see that the derivative of h is 1, so this becomes 1/8, and then dh dt. Don't forget the chain rule for these, okay? The derivative of r is 1, and then don't forget the dr dt. Now we know what dh dt is, and so we're going to actually plug in, and you can ignore this extra line here. But if we take the dh dt here and we plug in for dr dt, we get, remember that it's negative, right? So we're going to plug that in. So we get that the dh dt is negative, right? That's going to be negative 4/15 feet per minute. Okay. So now that we got the HTT, we're going to go back to the volume rate equation, and we're going to plug in what we know. Okay, so let's go ahead and plug that in. So if we plug in the radius and then the dr dt and then the dh dt, so we're taking this and we plugged it in here. We get a volume rate of negative 9.49 feet cubed per minute. All right, so the water level is draining at that rate. So it's a slightly more difficult problem, but it's not difficult at all. Just use the similar triangles in order to get the dh/dt. All right, so let's look at another example. So let's say we have here a pebble that is being dropped into a body of water. It causes ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a rate of 1.2 feet per second. So here they mentioned that it's increasing, right? So that means this is a positive rate. When the radius is 3 feet, at what rate is the total area A of the rippled water changing? So we know that this is in the shape of a circle, right? So so you can hopefully you can kind of see the circle that I'm doing. So that's a circle with a certain radius, right? And so we know that we could find the area of circle. So we know the area of circle is pi r squared. And so we can take the derivative of that with respect to time. So there's the concentric circles here that that is in the diagram. So we got that the radius is 3 feet, but that varies with time, obviously, as the circle spreads out. And so the derivative of the area equation, remember pi is a constant, so we can actually pull that out. We can ignore it. So we can just pull the pi out. And we know that the derivative of r squared is 2r. But don't forget the dr dt because we're using the chain rule. So it's going to be, in this case, 2 pi r. Let me just erase that. So 2 pi r dr dt. And then we can plug in the radius is 3 feet. And then, so this is what I'm saying is that you don't plug in for r until the very end, right? Once we get the rate equation, and then we know that this is positive, right? And so we do the math, we get about 22.6 square feet per second. So that's how much the area is increasing of the water ripple. All right, pretty straightforward, nothing crazy to do here. All right, so let's look at some more examples. So example 4, air is being pumped into a spherical balloon at a rate of 5 cubic feet per minute. So, so that's 5 feet cubed per minute. So find the rate of change of the radius when the radius is 1.5 feet. Okay, and so air is being pumped in there. So this is a positive rate, right? And so what this is air being pumped in at that rate, and that's a cubic feet. So that means that's a rate of change of volume. So they gave you dV/dt right there. All right, so that's important to know. So we know that the volume of a sphere, we're assuming that this balloon, well, it says it's a spherical balloon, so we don't have to assume that it's a sphere. It tells you. So we know that the radius or the volume of a sphere is 4/3 pi r cubed. So if you know that equation from geometry, you can go ahead and take the derivative of that with respect to time. Remember, the 4/3 and the pi is just a constant, so you can ignore that. The derivative of r cubed is 3r squared. And then don't forget the dr dt because of the chain rule. All right, so we bring the, and so notice that the 3 that you bring down, so when we have 4/3, so let me just show you the work there. And then you bring down the 3 from the 3r squared, right? Or the r cubed. So then it looks like that. And then the 3's cancel, right? So you get 4 pi r squared. And then, of course, you have your r prime as well. So that's the dr dt that I include. Okay, so just make sure you include your time derivative of r. And so now you're going to plug in your radius. Your radius is 1.5 feet. According to the problem, and then your dr dt, that is what we're looking for. So we need to actually solve for this, right? So that means we're going to divide by 4 pi r squared on both sides. All right, we know the dV/dt because they told us here, so we're going to plug that in. So we got 1/4 pi, 1.5 for the radius squared, and then the dV/dt is 5. And so notice that this is foot squared, and then this is foot cubed. So that becomes foot per minute. So that makes sense. So the radius has to be feet per minute, right? The rate of change. So it's changing by that many feet per minute. So it's going to be about 0.18 feet per minute. All right, so that's how much the radius is increasing. All right, so I also got yet another example. I find that it's good to do a lot of examples because since they're word problems, students struggle with the setup. So we're going to make sure that we do as many problems as we can. So we got a camera at ground level is filming a rocket at liftoff. The rocket is rising vertically according to the equation s equals 60t squared, where s is measured in feet and t is measured in seconds. The camera is 2,500 feet from the launch pad. Find the rate of change in the angle of elevation of the camera 12 seconds after liftoff. All right, so we're going to draw this triangle here so you can kind of see from the diagram. So the camera is over here in this position where that blue dot is, right? And the camera is pointed at the rocket and it's changing as the rocket is going up. We can see that the angle is changing. Okay, so we know that the angle is increasing as the rocket is going up, right? And so we know that the camera is placed 2,500 feet away from that launch pad. All right, so first off, we know that the distance from the camera to the rocket in the air is given by the Pythagorean theorem, right? So remember, it's going to be s squared plus 2,500 squared equals, and let's call that distance d, equals d squared. Okay, and if we take the square root of both sides, we get this expression. Okay, so that's by the Pythagorean theorem. So we know that that is my expression for the distance from the camera to the rocket. And we're going to need that later because we're going to plug in, we're going to try to use that to equation, right? We're going to use these equations in order to solve. So we know that from this right triangle here, this is a right triangle, that if we that if we use a trig function, tangent is opposite over adjacent. So we got opposite is going to be s, and we got adjacent is 2,500 feet. So we have tangent theta is s over 2,500. So that's sort of like our setup equation that we're going to need. That's our first main equation. Now we're going to take the derivative. So we're going to take the derivative of that. Because we're trying to find the rate of change in the angle of elevation. So we're trying to look for d theta dt. All right. So we're going to take the derivative of this equation on both sides, a time derivative. So now the derivative of tangent is secant squared. So we get secant squared, but don't forget the d theta dt, because this is what we're trying to get. We're trying to solve for that. All right. And then the derivative of s is just 1, but then you have 1 over 2,500, right? Don't forget the ds dt. Now we know we can find the ds dt using this equation right here. So we're going to use that. Okay. So let's go ahead and we're gonna. Well, actually, not this equation per se, because they actually give you s. Let me write it down. So here it is. So right here they give you the equation for s is 60t squared. So we're gonna actually plug that into there. Okay, and then we're gonna take the derivative of that. So the derivative of 60t squared is 120t. Okay, so we take the derivative of that and we get 120t. Then we got to get this by itself. So I'm going to divide both sides by secant squared. And so I get this equation for d theta dt. Remember that the inverse of secant squared theta is cosine squared. So if you move it over to the other side, it just becomes cosine squared. All right. And then we're going to go ahead and solve for, we're going to need to figure out what the theta is. Okay, so we're going to need to figure out what is theta, because we won't be able to solve for d theta dt if we don't know what theta is. So this is where we use the right triangle. Okay, so using this right triangle from the original picture, we can see that cosine is adjacent, is adjacent over hypotenuse. So that's what we're going to say. We're going to say cosine is adjacent, which is 2,500 over hypotenuse, which is the s squared plus 2,500 squared. And then we're going to take that and we're going to plug it in to here. And then remember that that's squared, so we have to make sure we include the squared, because we got to square the cosine, and that takes care of that. All right, so now we got the theta, the cosine theta part taken care of. We got the we plugged in. Now we need to plug in for the time. So it says that the time is 12 seconds after liftoff. So that's what we're going to plug in for t here. So we're going to plug in the time there. All right. Okay. Oh, by the way, this is a typo. This should say 10 seconds, not 12. So let me change that to 10. So I apologize for that. So that's 10 seconds, not 12. So I apologize. So what's the angle of elevation of the camera 10 seconds after liftoff? So we're going to take that 10 seconds and plug it in for time. And we need to figure out what s is. We don't know what that is yet. So we're going to plug it into the 60t squared equation. We're going to plug in 10 for the time. Okay, and that'll give us 6,000 feet. And then we'll plug that in for s. And then we'll have everything we need. So we have the s now, which is from the 60t squared equation. We plugged in for time. We have the time, which is 10. And we have everything we need, so then we can solve for d theta dt. So this problem is more involved, but it's not too crazy as far as the math is involved. I mean, there's a lot of different things, elements, but when you plug it in, you do the math, you get about 0.071 radians per second. Okay, so hopefully that made sense. I know there's a lot of moving parts there. All right, thank you for taking the time to watch this video. I hope you learned something new, and as usual, I'll see you in the next one.